Okay, so this is part 137. It's line 18A 3W, uranium neutrino split, Z bosons, weak atomic 5G UFO Wow Seti. There's a Wow Seti signal there. And so we look up, this is talking about reactors, so I'm going to do some reading about the reactors, okay? Reactors, moderators. In a thermonuclear reactor, the nucleus of a heavy fuel element such as uranium absorbs a slow-moving free neutron, becomes unstable, and then splits fissions into two smaller atoms, fission products. The newly released fast neutrons, moving at roughly 10% of the speed of light, must be slowed down or moderated, typically... I just realized I don't have my lamp on. That's why it's so dark in here. Sorry. There. That's better. Just trying to figure out why the screen's so dark. Okay, sorry about that. I don't know where I was. Okay, so the newly released fast neutrons moving at roughly 10% of the speed of light must be slowed down or moderated, typically to speeds of a few kilometers per second, if they are to be likely to cause further fission in the neighboring U nuclei and hence continue the chain reaction. This speed happens to be equivalent to temperatures in the few hundred Celsius range. In all moderate reactors, some neutrons of all energy levels will produce fission, including fast neutrons. And it talks about them being thermalized. In the CANDU reactor, there's a pressurized water reactor that can produce higher energy neutrons. There's a proposed water cooler supercritical water reactor. The proportion of fast fissions may exceed 50%, making it technically a fast neutron reactor. That's the one we want to look at. A fast reactor uses no moderator, but relies on fission produced by unmoderated fast neutrons to sustain the chain reaction. Basically, they create their own chain reaction. They don't need a moderator to speed them up. In some fast reactor designs, up to 20% of fissions can come from the direct fast neutron fission of uranium-238, an isotope which is not fissile at all with thermal neutrons. Moderators are also used in non-reactor neutron sources such as plutonium-beryllium and spatial sources. February 17th. My thoughts. If uranium absorbs a slow-moving free neutron, then uranium-238 plus a neutrino, slowed down by cooling the plasma with the invention found, plus unstability, plus splits into two smaller atoms, fission products. So we have an idea of how to transfer energy from a neutrino to a lepton, and now this says you can use uranium to split a neutron. Can it split a neutrino into smaller particles, thus doubling the amount of energy produced? Then we need to speed it up, cause more collisions with the laser beam so we can generate more energy within the argon gas. I did a Google on neutron, neutrino to see how they are related. And it says that neutrinos are not affected by an electric charge, so in order to get it to split, we'd have to use a weak subatomic force. So I looked further. Quote, neutrinos do not carry electric charge, which means that they are not affected by the electromagnetic forces that act on charged particles, such as electrons and protons. Neutrinos are affected only by the weak subatomic force of much shorter range than electromagnetism and gravity, which is relatively weak on the subatomic scale. They are therefore able to travel great distances through matter without being affected by it. Quote. So the next quote is, in the standard model of particle physics, the weak interaction is theorized as being caused by the exchange, emission, or absorption of W and Z bosons, and because it is a consequence of the emission or absorption of bosons, it is a non-contact force. The best known effect of this emission is beta decay, a form of radioactivity. Beta decay was also mentioned in the neutrinos. The Z and W bosons are much heavier than protons or neutrons, and it is the heaviness that accounts for the very short range of the weak interaction. So when they interact, they do it within a short range. and don't last very long. Z bosons came up a few videos ago, so we have a new formula to try. Z bosons plus neutrinos plus short-range pulse of laser beam equals new type of energy. Search Z bosons in Wow Seti notes. It's on 14 modules. It comes up on Go to the Light, which is not titled or filmed yet. It's in lines 15A, 16A, 24, 15B, 15E, 15F, 15B2, 16B, 15NN, 18X, 18A3M, 18A3T, which is the latest one that I did, and then 18A3W. And line 18A3T is the gluon spin quark Z bosons Erik coefficients hadron rings Wow Seti. That's the latest in this data. Again, I'm only on this line 18A. I do have up to line 27, so this information could change. So another quote is, Tabitron through collisions of the particles, quarks and gluons, inside the proton and antiproton beams. Once Z bosons are produced, they decay into lepton, anti-lepton pairs. Example, electron, positron, or muon, anti-muon. So the next formula that you want to try is lepton energy plus transferred from plus neutrinos plus collision plus particles plus quarks plus gluons plus proton plus antiproton plus beam plus laser plus Z bosons plus decay plus muon equals accelerated plasma. So Google Tabitron. I thought it was a type of particle. I didn't realize it was actually it's a circular particle accelerator in the United States, and it's at the Fermi National Accelerator Laboratory called Fermilab, and that's east of Batavia, Illinois. It is the second highest energy particle collider in the world after the Large Hadron LHC. And there's a picture of it, which for some reason is very small instead of big like it should be. So let's make it bigger. Look at this thing. It's huge. Absolutely huge. Background. So the Very Large Hadron Collider is a name for a hypothetical future hadron collider with performance significantly beyond the Large Hadron. So this is something they want to build. That's the one they have now. But they want to build a bigger one, and it was put on the back burner because it would cost too much money. It would take them too much time to build it. So I'm going to reading the quotes from the data above, and this stands out. A pressurized water reactor, PWR, a considerable portion of the fissions are produced by higher energy neutrons. High energy neutrons is the ultimate goal. Maybe they already know how to convert them into energy, but it's not openly discussed. They want to figure out how to split them, and I've created several formulas that might work. Quote, in the proposed water-cooled supercritical water reactor, the proportion of fast fissions may exceed 50%, making it technically a fast neutron reactor. And then I have a fast reactor uses no moderator, but relies on fission produced by unmoderated fast neutrons to sustain the chain reaction. My thoughts continued. Fast fissions may exceed 50%. A fast neutron reactor, a no moderator, so we're looking at fission plus fast neutrons plus question mark for a chain reaction. My idea, fission plus fast neutrons plus leptons splitting to transfer energy plus quarks plus pions plus the use of kinetic energy. Let's Google and see what comes up. When I say we're going to Google it, I actually put all those words together, throw them into Google and see what comes up with it. So, quote, the first artificially induced nuclear fission reaction was achieved by Enrico Fermi in 1934, although at the time he did not realize that fission had occurred. Fermi bombarded uranium with neutrons and produced radioactive products that emitted B particles. Okay, so I'm not going to go into everything he says or did. He does talk about other elements. He created some other elements, atomic number 93, known today as Neptunium-239. He also produced other elements like Ba141, Kr92, and all those ones there. Okay, and he suspected these lighter elements were the products of the splitting of the uranium nucleus. So basically everything that splits seems to create something else. So February 17th, my thoughts continued. According to this U-235 nucleus absorbs a neutron. The nucleus splits into two smaller nuclei. What are their names? And emits 1, 2, or 3 neutrons in the process. Ergo, nuclear fission is the part of the equation. So when I googled it, this is what came up. Quote, energy from fission. The binding energy curve shows that a heavy nucleus has a binding energy of about 7 MeV per nucleon, whereas nuclei of elements with roughly half the mass number have average binding energies of about 8 MeV per nucleon. Now that's weird. We've got elements that are half the mass of the heavy nucleus, and they actually produce more energy. Why is that? Thus, when the heavy nucleus splits to form two lighter nuclei, there is a release of about 1 MeV of energy per nucleon. Oh, that's why. Okay. So for a heavy nucleus of 200 nucleons, there would be a release of about 200 MeV of energy from each fission. Okay. Clearly, tremendous amounts of energy can be produced from sustained fission reactions. Okay, so they're talking about creating more energy. And he's talking about coal. And this basically equals 3 million kg of coal. So he's showing an example of fission reaction. And it says we can calculate the energy released in this reaction in a couple of different ways. We can either determine the difference between the binding energies of the products and reactants, or we can find the difference between the masses of the products and reactants and then convert this mass difference into its energy equivalent using Einstein's E equals mc squared equation. And let's go down here. That's all I'm going to read about that. So here are the tags for this video. Okay. Lots of tags. And we'll go on to the next one.